Okay, I'm going to go over the answers to the 5.2 quick check. So the first thing is to write the combustion equation for butane. So butane, we're going to write down C4H10. And since it's combustion, we're going to add oxygen, O2. We're going to turn into CO2 and H2O. Okay, I would do the carbons first. I have 4 carbons here, so I'm going to say I have 4 carbons, 4 CO2s. I have 10 hydrogens over here, so that's going to make 5 O2s. And if I count it out, I have 4 times 2, I have 8 oxygens here. 5 times 1, I have 5 more oxygens there. Okay, that equals 13, so I could write 13 halves O2. Now, this is a case where I would really rather have this in whole numbers, because when I do my conversion factor, it's going to be a lot better that way. So I'm going to double everything, and I'm going to say 2 C4H10s plus 13 O2s turns into 8 CO2s and 10 H2Os. And I'm going to be using those numbers as I do the problems. Okay, down here we want to do the equivalent quantities. So C4H10, how many grams in 1 mole? Okay, that means we have to go back and figure this out. So I have C4, I have H10, using the periodic table. I'm going to use 4 times 12.01, and that's going to be 48.04. And 10 times hydrogen, which is 1.008, and so that's going to become a 10.08. Add that together, I'm going to get 58.12 grams per mole. So right here, this would be 58.12, and I'm going to use that as a conversion factor. Okay, moles of CO2 to moles of O2, those are going to be numbers from my balanced equation, and I have 8 CO2s, and O2s I have 13, 8 to 13. Now I could have used the numbers before, but then it would be 4 to 13 halves, and that's going to make a kind of a funny looking fraction, so it's easier to work with whole numbers. Okay, molecules of water in 1 mole of water. Okay, that's our Avogadro's number, 6.02 times 10 to the 23. Okay. For grams of CO2, I have to do that. So here's a C, 2 O's. So this is going to be 1 times 12.01. Okay, which will obviously would be 12.01. And this will be 2 times 16.00, which would be 32.00. And that's going to end up being 44.01. And that's my conversion here, 44.01. Okay, now I'm going to head back here, moles of O2 to moles of C4H10. Okay, well, from the balanced equation, I have 2 moles of C4H10 and 13 moles of O2. Okay, liters of O2, that's our beach ball number, so that's 22.4 liters for 1 mole of oxygen. And the last one here is C4H10 to H2O. Okay, 10 H2Os, 2 of those, so 2 to 10. Now, if I hadn't used that, if I'd done 1 to 5, that would work fine for that one. Okay, so those are all those numbers. Now we can do Stoic Geometry, and these I had to go ahead and write them out by hand and scan them in because there's a lot of information. So we say here, it says how many moles of C4H10 to produce 3.55 moles of CO2. So we're given 3.55 moles of CO2. The number's important, the unit's important, and the compound's important now. And we're going to look for moles of C4H10, so moles of C4H10. So I'm going to write down my given number. And we can think about this too. I'm starting with moles, and I'm going to moles, so that's only going to take 1 conversion factor. So I expect this to be a 1 conversion factor problem. And going back here, I can see how I just use 1 conversion. My mole-mole ratio, and that comes from my balanced equation. So there are 8 moles of CO2, that's my desired, and 2 moles of C4H10. So 2 and 8. Again, if I hadn't doubled my thing, I would have had 1 and 4, same answer. And when I multiply that out, I get 0.1 0.8875, or if I round that off to three significant figures, 0.888 moles of C4H10. That's the first problem. Okay, the second one says, what's the volume of CO2 that can be produced? When we say volume, then we're talking about liters. Okay, so volume is a Q word for liters, mass is a Q word for grams. And the fact that it says at STP, that's kind of a dead giveaway. We're going to use 22.4. And our given value is 20.8 liters of O2. So I'm trying to get to liters of CO2, starting with liters of O2. So here's my equation. Okay, I'm going to go here and I'm going to say I'm starting with liters. And I'm going to go to moles. That's going to take one conversion. Moles to moles of my new chemical. And then back to liters. So that's going to be a 3 conversion factor problem. Liters to moles, moles to moles, moles to liters. Okay, so we've 3 conversion factors. So I'm going to go from liters. I'm going to use 22.4 liters per mole. Then I'll use my mole to mole conversion. And again, CO2 and O2, I'm going to use 18 and 3. That's from my balanced equation. And I'm sorry, 13 and 8. And then again, to go back to liters, I need 22.4 liters again. So my final answer, I'm going to do 20.8 times 8 times 22.4 divided by 22.4 divided by 13, and I get this value. Now you might notice mathematically that 22.4 is actually canceled out as well. So the liters cancel out, moles cancel out, moles cancel out. So 20.8 times 8 divided by 13, this gives me this answer, 12.8 liters of CO2. Now the last one is, what is the mass? Mass is a clue word for grams, and we're trying to get the molecules. So starting with grams, I'm going to go grams to moles, that's one conversion. Moles to moles, that's the second conversion. And then I want to get to, I'm sorry, it was wrong. Okay, I'm going to change color. Starting with molecules, my given is molecules, molecules to moles, moles to moles, and then moles to grams. So again, it's going to be 3 conversions. And here we go. So what's the mass? So when I do this, I say, okay, I have 4.50 times 10 to the 22 molecules of H2O. That's my given. And then I'm going to use my 6.02 times 10 to 23 molecules of H2O per mole of water. Then I'm going to go 10 moles of water for every 2 moles of C4H10. And then the last one is 2 moles of C4H10, 1 mole of C4H10 weighs 58.12 grams. So notice that this conversion factor and this conversion factor are always 1 mole. This one can be any number of moles because it comes from a balanced equation. Now, when this is all said and done, I did make one math error when I wrote it out. And I thought that this was a 23, not a 22. So this number is too large by 10. So the actual answer is 0.8689 grams of C4H10, which we might want to round off to 0.869 grams of C4H10. So both of these are the 2 good answers here. Okay, and that is the quick check.